And with this, it's a pleasure then to give the floor to work package 4 lead in Hexa-X-II, so Ahmad Nimr from TU Dresden. Please go ahead.
Thank you, Mikko. Hey, good morning and welcome to this presentation. My name is Ahmad Nimr from TU Dresden, co-lead of work package 4, together with Nurul Mahmoud from University of Oulu. So in this presentation, I will give an overview of the work related to radio design and key enablers that were investigated in Hexa-X-II project, particularly in work package 4. Yeah, first, I would start with the big picture overview of the radio system that we come up with through the work in these projects. So these studies, the studied radio enablers are mapped to holistic radio design framework, highlighting different radio component, including channel, radio unit, physical layer, MAC layer, and upper layer protocols. The goal then is to select and optimize end-to-end design, taking into account cost and energy efficiency. We categorized the enablers into 5 groups. The architecture and deployment, consider the impact of radio front end and propagation. Then we have radio link modeling that include the channel model and hardware models, as well as other modeling related to the signals. Then we have a wide range of focus on signal processing and algorithms corresponding to phi and resource allocation. The 4th category is related to flexible spectrum access, which covers aspects related to sharing and low latency access. Then we have on top of this radio, we consider some complementary solutions for trustworthiness and inclusiveness. So here we put things together. So this slide summarizes the interaction among different radio components, reflecting like different level of flexibilities in modulation and coding and resource allocation, the configuration of the RF transceiver in terms of carrier frequency, bandwidth, active transmitters, in addition to controlling the beamforming and erase if it's also to be deployed. Then other degree of freedom from the radio infrastructure perspective result from the functional split that could realize various aspects, such as centralized RAM, carrier aggregation, as well as like from pure physical layer, different options for distributed MIMO, either decentralized or centralized in the context of the processing, centralized processing or distributed processing. So this gives the overall picture of the radio, and then in relation to the system blueprint that is proposed by Hexa-X-II, the radio aspects contribute to the access part in the infrastructure layer, and in the network functions layer, it contributes to the RAN functions as well as localization and sensing. With this overview, then I spend the remaining time of this presentation on providing an overview of the different technical contribution, highlighting some aspects because we have studied so many topics. So I will just pick up some of them, and the details are in the deliverables. Yeah, so starting with the channel modeling, the focus was more on developing a methodology and sounding platforms. So these can be applied to various frequency bands, sub-terahertz, millimeter wave, FR3, and so on. And we did in the projects of several measurements, some related to the sub-terahertz, such as the material wave interaction, near-field models, and additional work consider the channel sounding in FR3, and also there is a study on the JCAS channel model that's detailed in one of the deliverables. MIMO is an important topic, so we have covered various topics related to massive MIMO architectures, mainly the well-known hybrid beamforming architecture. Also, some studies about fully digital approaches with low-resolution DAC ADCs. So that was mainly focused on the sub-terahertz, but the transceiver design methodology presented in this work can be applied to various frequencies, including the sub-terahertz, millimeter wave, and FR3. And we looked at also various distributed MIMO architectures and transmission schemes, such as the ones to improve the coverage, or using distributed MIMO in the context of JCAS. One of the other ideas related is on using movable and rotatable access points, and this shows some potential in improving the capacity when we consider the dynamicity of users and environment. RIS also was investigated in various settings along with distributed MIMO to overcome blockage. So one of the key takeaways from the analysis related to blockage, it shows that RIS should be placed closer to the transmitter or the receiver, and active RIS, in the sense that the one that can also amplify the signal, is more significant in improving the link quality when there is a medium blockage. But purely passive RIS without any amplification could help only in the conditions of strong blockage. In relation to waveforms and modulation, here were some studies related to sub-terahertz and to tackle mainly the hardware constraints. So some focus on learned constellation, others on polar constellation. Then there was proposal for waveform improvement based on the extension of OFDM, and there is a proposal on a general form of multicarrier called adaptive multicarrier modulation. So that could be tuned to reproduce different types of linear waveforms. And there is also one study related to coding, and particularly in particular optimizing the LDBC code matrix, and the optimization aim to reduce the computational complexity and therefore to reduce the latency. A wide range of AI ML studies are presented, so covering a lot of topics, and this was one of the most active tasks actually in the projects. So there are studies covering learned waveforms, CSI feedback and prediction, resource allocation, optimization for distributed MIMO, and also proposal like using AI/ML for hardware impairment compensation. So the main goal was to evaluate the potential of AI/ML in enhancing the air interface, or maybe mainly the existing air interface, such as reducing signaling overhead, reducing computational complexity, improving performance in comparison with the conventional approaches. So in fact, anything related to signal processing actually can try out also the machine learning stuff. Regarding joint communication and sensing, we focused on providing a holistic view on JCAS from two aspects. So on the one hand, by exploring the deployment options where sensing is performed using the communication infrastructure, and is associated with other enablers. So we studied like different enablers like NTN, MIMO, RIS, what kind of combination can make sense to be used for sensing. And on the other hand, algorithms were developed for using the communication signals like OFDM, as well as optimizing the resource allocation for sensing functions, for improving sensing accuracy, for delay, for Doppler angles, and so on. And the details about this holistic view is under preparation for a very, let's say, comprehensive tutorial paper, and this will be hopefully published by summer. Yeah, for spectrum access, also a couple of areas were covered, and in particular, some studies on spectrum sharing with fixed satellite, multi-rad spectrum sharing, some studies on NTN radio interference enhancement, mainly focusing on mobility part as well as interference mitigation. And for trustworthiness from the radio perspective, we considered some studies related to the impact of different jamming signals on communication performance. So there was some analysis of that. Work related to jammer localization, analyzing JCAS privacy and security. And in the final deliverable, there is a proposed resilience by design framework to have also some holistic view on resilience. Finally, here I would highlight a couple of the activities related to proof of concept. And like some of them are for like hardware platform for evaluating some performance, some other are simulation, and there are also demonstrators. So for instance, we developed flexible transceiver platform that used for evaluating different baseband algorithms by with different RF frequency bands. So there are some tests for the sub-terahertz, for FR3, for millimeter wave using these. There's work on MIMO testbed that is used for also the assessment of various aspects of distributed MIMO, like access and backhaul. This is also with EMF assessment framework for DMIMO, but this is a simulation framework. And there were demonstrators for the native AI air interface, as well as for the bistatic JCAS. And some of this, also this work will be presented again in EUCNC this summer. Yeah, so further details on this work you can find in the public deliverables related to work package 4. So mainly D4.2 have the full description of the enablers from the beginning, with some results in D4.3, and the conclusions and final results are presented in D4.5, and this will be available by March. This concludes my presentation. Thank you for listening.
Yeah, thank you, Ahmad. There is so far no specific questions to this presentation in the chat, but maybe some of them arrive. And there would be possibility for, if you want to pose an audio question, you can raise your hand. There is time maybe for one. Yeah, is it Mitch, please?
Yes, thank you, Ahmed. There's a lot of work your team has been doing. That's great. One part about this flexible spectrum, is that also equivalent to this so-called spectrum sharing? Is that a work on this? Is that under the same topic? Thank you.
I don't get the question very well.
Okay,
Could you
well, there's the one slide talking about spectrum, flexible
Yes.
spectrum or something. Yeah, this one. Is this equivalent to the so-called term spectrum sharing? Yeah, because in the North America, we actually treat this as a very big subject because can
Okay.
we maybe use a different bands, and then we are using the same spectrum for the applications. Yeah.
Yes, exactly. So this is about that exactly. Like, for instance, when talking about sharing the spectrum, so the same spectrum for fixed satellite to be used on the ground.
Okay.
And
maybe
how to deal
actually-
with the interference. Yes, Mikko.
Actually, from one question to you, Mitch, then that concerning the spectrum sharing, and there has been long time quite an attention on that in North America, of course, in other regions as well. How do you see the commercialization of that in the civil area?
Well, that's a good question. But then I think right now, part of it is because of ownership of the spectrum. So if you have a spectrum, do you really want to share with other people? And then the other one is that when you share it, can you make it more efficient and then in a better coordinated way? So that's a subject that the people are still talking in the North America. I would say probably your understanding is probably as good as mine to see the future of that. But I think that's one way to encourage collaboration and special efficiency, right?
Yeah. Okay.
Thank you.
Thanks for the question, Ahmad. Thanks for the presentation. And if we then move to joint communication and sensing architecture, so Madhusudan from the 6C DISAC project, please.
Hello, yeah. Can you hear me? Yeah.
Yes, can hear and see.
Okay, so I will just share my slides. One. Okay, I put it on slide node. Is that okay?
Yes.
Yeah, okay. So I'm Madhu from Orange, a leader for the WP2 in the 6C DISAC project, which deals with distributed intelligent sensing and communication. Because there are a number of contributors to this work, which I've listed here. So the project started in 1st of January last year. So we are just at the end of we have finished 1 year. You can see the various partners in this. In the interest of time, I won't list them all. So there's Emilio, who will be also involved with the 6C goals. I'm mentioning this because for the semantic part, we collaborate with the 6C goals. And there's, of course, Hank as the technical manager. So what are we talking about? We are talking about moving from just monostatic, bistatic to multi-static, but not just the distributor is not just multi-static, but also the fact that for any real service, it's over an extended area and over extended periods of time. So handover of passive objects is also something that's done, and all the distributed communication that happens with that. And semantics, as I mentioned, is also something that we're exploring in the project. So coming now specifically to the architecture part, which is what I will be talking about in this presentation. So the challenges for the distributed part that we envisage are finding a parsimonious data representation for distributed processing, because the raw sensing data is voluminous, and depending on the service requirements, we need to find the right balance between how to object the sensing performance that is needed with the storage and data exchange that needs to happen. And then, of course, ensuring the continuity of sensing service over a large area needs that we need for passive targets that we need to handle mobility to handover. Then, of course, there's the efficient allocation of resources for both sensing and communication, meeting the KPI and KVI objectives for the different use cases, and of course the integration of a wide variety of network devices and elements. In December, we published a deliverable which is available on the SNS for the SNS projects in the repository. It's not as it's publicly available because that will happen after the internal review, which was a few months down the line. But for people on the SNS projects, the deliverable is accessible. So in the interest of time, there are four what are you calling enablers, things that meet these challenges that I've just listed. One for the data processing, data representation, the other for tracking and handover, and then for the support of heterogeneous devices and the semantic reasoning and control. I will be explaining it in the following slides. So what are we talking about when we talk about data representation? This is the form in which the data is stored, processed, and transmitted between different nodes. And as you can see in the picture, a whole bunch of choices are possible, and this is far from exhaustive. Even more are possible. You could just send the raw data, you could quantize it and send the quantized data, which is more compressed. Or typically, like what happens with radar, you have this range Doppler maps, and which could be transmitted. Or you could transform and then locally perform the peak detection and send what's a point cloud, which is an estimate of the number of targets that you're seeing and their parameters such as range, angle, Doppler, and so on. Or a whole bunch of high-level representation, quite a number of AI-based representations, parametric representations, which take care of extended objects. And from the architecture point of view, what we do need to do is to decide, what will happen locally, what will happen at the network core or at the edge, and what form of data we exchange between them. And the goal in the project was to accommodate both centralized, hierarchical, or distributed processing. Just to make this a little bit concrete for people, this is as people in Hexa-X-II may be familiar with. It's kind of sort of inspired, borrowed from that. So what we'll be adding more specifically is compared to what's been done in Hexa-X-II is that there is a set of UEs and a set of base stations. So these are the sensing nodes that will be enabled. So in the setup, we have a group approach, group of nodes that will participate in performing the thing, because we are both in a multi-static and in a mobile environment. And also what I just talked about, the data representation, that will also be negotiated in the negotiation and configuration that happens between the sensing processing, which in this case is being called the SEMF, sensing management function, and the SEPF is the sensing processing function. I'll be coming a bit into this, but just to make what I'm talking about in the data processing, data representation a bit more concrete, and putting it in the sort of Hexa-X-II kind of framework. So for object tracking and handover, so this would be, there are multiple sensing nodes, as you can see for the STX and SRX, that's the sensing transmitter and receiver, which are distributed around area, and the target is moving. We are talking about multi-target tracking here, so we have to estimate the number of targets, manage the appearance and disappearance of objects, track maintenance, and so on. And so this is a whole bunch of challenges, because this is the coordination between different sensing nodes that needs to happen. Handling target identifiers and a uniform data association. Where would that be handled? How will that be handled? And close to near real-time prediction and path estimation for objects that are moving, passive targets that are moving fast. And the actual handover procedure. So this is described a bit more in the D2.2 deliverable that I just talked about. This is just to give an overview here. And for the support of heterogeneous devices, we are talking about, like was mentioned in the previous presentation as well, the multiple different kind of antenna technologies that we might be using, massive MIMO, distributed MIMO, RIS, extremely large apertures, and so on. How do these fit in? Because some of them are capable of in terms of the achieving the actual performance, some knowledge of what the capabilities are needed to choose the right parameters. And of course, the more traditional multimodal sensors, which is such as LiDAR, infrared detectors, cameras, and so on, which needs to be handled. And in terms of the architecture, at the bottom you see the control modes and reconfigurability. So they could be either non-reconfigurable, reconfigurable after control, or autonomously reconfigurable. And the ones, of course, that are of interest from the architecture, the ones that are reconfigurable, and where and how that happens. Those are the topics we started exploring. Like D2.2 is a preliminary. Hello, I'm hearing some noise. Yeah, D2.2 is a preliminary deliverable, and we will be. Can you hear me all right? I'm hearing a noise.
There is unfortunately noise, so we are looking for to remove that.
Okay. Yeah. Sorry. I'll just go on. Yeah. On the semantics, I mean, this is just a quick overview. Emilio will be presenting 60 goals. So as I mentioned, we are collaborating with 60 goals on this. And I think Emilio will talk about it a bit more. There are two specific things we are doing in the project itself. The first one is the semantic aware adaptive waveform. That's a waveform specific for both communication and sensing, which is based on semantics. I don't have the time to go into it. And then of course the semantic RAN, which is more traditional one. I believe there's some work done in Hexa-X-II, but there's been specific ORAN based stuff using the semantic blocks, which has been done in 60 goals, and we are collaborating on the architecture aspects of it. So in terms of the architecture, it's the coordination that is needed between the different layers, the semantic layer and the RAN layer. Which means that there's some kind of a control plane that deals with this for the semantics, and also the resource allocation and orchestration mechanisms that happen, particularly in this ORAN-based approach. And yeah, this is what the sort of high-level architecture looks like. So that there are the sensing nodes that the STX and SRX, the RIS modules, the autonomous RIS controller, or the which I talked about a little bit, or the reconfigurable RIS controller, and the sensing could happen either the core, which is on the right, in the middle, or towards the bottom. The SEMF, that's the sensing management function, and the sensing processing function. Sensing processing function is where the fusion occurs. But what we have done in the project is to say that the sensing processing function, because in most devices, some kind of processing happens on the sensing side locally, So that's why we've introduced this notion of local sensing processing function. So this is what happens on the device itself, and of course there could be sensing done on the edge as well. So that is a very quick overview of what we have done. So if there are any questions, I can take them. There are some papers on the D2.2, of course, and there are some other papers which are available on the slides, which will be made available. But if you have any questions, I can take them. Thanks.
Yeah, there is in the chat, there is one question concerning slide 11, and based on the slide 11, it looks like that the functions here are core network elements. You can still take a look at the question if there is anything you would like to add to that. There is also.
Okay, go ahead.
So this, it's about the sensing management function, sensing processing function.
Okay, the sensing processing function is meant to be distributed, so it's not just at the core. It could happen locally or at the edge, and of course, the fusion will typically happen in the core. The sensing management function, as far as the current work suggests, would be in the core. For the moment, we are not planning on distributing it. That might evolve as the project goes on, but that's, yeah, so the answer is the sensing management function is in the core, but the sensing processing function is, we envisage it as being distributed. Sorry, and what is the second question?
That was the question. So it was these two functions. So that's why I was saying two. So there is also time for any audio questions. If you're interested, so please raise your hand. Yeah, Mitch, please.
Yeah, thank you, Mikko, and thank you for the presentation. Yeah, I always take this opportunity. If nobody raises hand, then I will. Right. So look at this chart. Yes, actually, it's kind of like it's very good that you focus on the radio based sensing. But I think in your presentation, you also mentioned about like using other sensing devices like LiDAR and stuff. Is that part of the project? And if that's the case, then do you have a very stringent requirement for synchronize those data you get from different source? Thank you.
Yeah, very good question. Yeah. It is not a major project part of the project, but it is a part of the project. It's true that in the first year we focused almost completely on the radio sensing. You're right. On integrating more LiDAR and cameras and other kinds of devices, it is what we envisage role for is first for the semantics to do the kind of fusion that is needed between the radio sensing and the non-radio sensing, and also on and related to that on AI/ML techniques for primarily from the fusion aspects. So that is what the project will be doing. Did that answer that, or are you a question, or did you mean something else?
Yeah, that's very interesting, because I think right now when we talk about the JCAS, one of the concerns is that at the current stage, the resolution may not necessarily achieve to the level that we want. So maybe there's still some way to go. But on the other hand, we can also take advantage of this like other means to help us. And I think that's probably what you mentioned in the semantic part. That part I haven't really touched much about it, so I'm going to look into that part. Thank you.
Yeah. Thank you. Yeah. Anything else?
Seems no other immediate raised hands. So I would then propose that we thank you, Madhusudan, and move to the next presentation. It's from the 6C Goals project. So Emilio, Calvanese, Strinati, please, the floor is yours.
Hi, everybody. Just 1 second. We'll share my screen. Okay, you should see my screen, right?
Yes.
Okay.
It's audio, video, and slide sharing all working fine.
Perfect. So thanks again for this invitation, Mikko, to the Hexa to organize this series of seminars that are actually very interesting for interacting between the projects. So my name is Emilio Calvanese Strinati. I'm the Future Wired System and Innovation Director at CIT, and also the coordinator of CG Goals, focused on semantic communication I was speaking about. CG DESAC, where actually you just have a presentation very clear from Madhu. Thanks, Madhu, for that. And Giyyarpuram, a new project in the framework of Europe and Korea, which also tackle the problems of semantic and AI in CG. So first of all, who we are. This is consortium composition. So I'm the project coordinator, and Professor Paolo Di Lorenzo from Kenichi is the technical manager. In the project, we have 11 consortium partners, one also coming from Asian affiliate partner, actually Singapore. We started in January last year. We finished December 2026, so we are less than half of the way. So why we actually consider this project, what we want to do, the major pitching reason, I would say, what if we can say less but understand more in an AI native system in which actually agents interacting between them actually are able to use intelligence to reason, to understand, and to also create and fear new ideas and connection and meanings in the data. So we oppose our approach to the classical approach, where that actually has been shaping generation of communication system, which we are kind of content-blind transmission without understanding approaches, where actually data is transmitted without the understanding of the prior meaning actually, and how actually is informative for the receiver, and how useful is. We also speak about pragmatic is for the end goal of the communication. So this actually, of course, enabled this approach to reach the level we have up to 5G, and definitely it has been and is very useful in terms of, say, classic communication from a point of view where actually intelligent agents are not necessarily part of the play. And in this case, what we actually experience, we have been fighting for, is this large volume of data, this problem about reliability on the communication level. And actually, what we are asking somehow is to be very precise, but without having an idea exactly what we have to send. So indeed, the question is, can we move from communication reliability to the end goal reliability? Can be inference reliability, can be also reliability in terms of decision making, and so on. And in this direction, we leverage on this this paradigm that actually had been already pointed out by Shannon more than 75 years ago, was actually instead not only consider what we call the technical level, the level A, where actually we are concerned about how accurately can symbol of a communication be transmitted. We also have a second level, which is more related to the application level. Indeed, how precisely do the transmitted symbol convey the desired meaning, indeed, for the application. And then there's a third level, what we call the effectiveness level, related to more the intent on the goal of the communication, where actually the question is, how effectively does the received meaning affect to conduct in the desired way? So actually how in the environment where your agents are playing, we are operating, actually the information that you structure, given way you receive with a given precision, indeed is useful and needed to achieve a goal. So also being 75 plus years old, actually in truth, we have been neglecting this approach for a long time. And we are now considering an overall system in which we have these three layers together, and indeed where we have a physical layer with all the network traffic engineering, with all the coding part, modulation, synchronization, all the things we do since in tens of years, which are fundamentally important. But we add on top of this part of the semantic part, where actually data is interpreted by an AI agent. Probably we use transformers, graph neural networks, and so on. And actually, it's then received by another agent, which is intelligent as well. We actually try to understand in the correct way. But in between of them, there's what we call this semantic channel. There's actually this logical channel for which either if information is correctly received might be not understandable. I make all this example. We say let's meet in a weekend. For some can be Saturday and Sunday. For some it could be Friday, Saturday, depending on the culture you come. So the same way. So there's a kind of need of a plane, of a architectural plane for which you have interaction, and you explicitly you have some pilots to understand the logic of the receiver, the logic of the transmitter, how those are aligned. So so the what to the project indeed is the really key concept to work on this semantic approach to communication, and then actually to lay out the theoretical, algorithm, and operational foundation for a native communication system. And actually, the aim is to, first of all, to compress. That's something that most of the people understand in the first hand. So you actually, because you're able to reconstruct, so you add kind of new layers of coding, that you're able to compress more by being still reliable. And then indeed you send less, understand more. But you can also do what we can call continuous learning, the way that actually the communication itself is a way to stimulate also and update the models, the AI models are the transmitted to the receiver. So we facilitate knowledge sharing between heterogeneous and disparate users. And then also the thing to stimulate reasoning, again, in the way that actually there's a way for which the receiver can, for example, also the transmitter can compose different kind of concept that they're available, the meaning, for creating new meaning out of the data received. And so this is a classical example I give in terms of which kind of reliability we add in here. I mean, if you try to read this text, which is completely madness in terms of precision of say level of noise we have in the communication, where there's almost everything is wrong, but still there's a part of the words are correct. For example, the first letter and the last letter are mostly correct. The length of the words is roughly the same. So in this case, you're able to read. And actually, what we are using here to relax some constraint at the physical layer, because we can accept the level of noise, then we show that, for example, we can reduce the surface of an antenna we use for transmission. We can reduce also the signal to noise ratio we need for transmission, and so on. So actually, we can have a not so good signal received, but still having this additional level of a correction from the semantic part, we are able to correct that. So indeed, this project is based on two major paradigm shifts for the 6G. First of all, is what we call this goal-oriented communication, where actually we come from this data-oriented communication blind approach to a goal-oriented effect transmission, where the communication is shaped to achieve a goal and accomplish a task. As an example, for example, we can tune the quantization precision of the system, because sometimes you don't need to be that much precise in terms of the goal or your communication, and so on. So actually, you can protect, you can select, you can filter differently depending on the task. And second part is actually what we call the A-native semantic communication, as I said before, where we move from content-blind raw data, teletransportation, transferring, to share only what cannot be deduced or inferred by AI, can be generative or not generative. It can be with a goal or not a goal is defined. So different cases are possible. So in this case, the game is really to identify the relevant needed information to recover the meaning intended by transmitter at the receiver. So there is also this problem, again, to have a common sense between transmitter and receiver, for which we use the same logic. And to cite Voltaire, a French writer, the common sense is not a common, and now we have this problem of this semantic channel that sometimes we need to align actually transmitter and receiver. So as I said before, we do study the foundational principle of the semantic communication, and also we are very concerned about the gain in terms of sustainability at this trade-off between adding more processing, indeed, with this approach, but actually compressing a lot and reducing a lot the training time and training phase of AI in these cases. And actually, this balance is something that we are measuring is going on. So we have not results. The first result shows that we have something very interesting here, because actually we have something around 10% of the augmentation of processing costs, but at the same time, with something about 1,000 of compression rate. So indeed, you can see that we have a very large gain, but this measure will come probably in 6 months from now. And then actually, we need to define architecture. And out of different points of architecture we're studying here, the important thing is to have this kind of what we call the semantic plane. Some people can call that, for example, in ETSI, ANI, they call that the AI plane. The idea is that we need a plane where actually we can also exchange logical information and control messages. And one also big problem here is actually to ensure the coexistence between semantic empowered, not semantic empowered users, or goal-oriented, not goal-oriented users in the same system. Indeed, also enable the interoperability between different types of users here. And then we also study how do we extract, represent the user semantic in a very precise way. And to that way, we have a fundamental theoretical study about the causal representation rate to the data. And then actually, we also use generative AI to indeed produce something which is actually application-friendly, user-friendly. So we do actually compress, and we do actually form the data also according to the causality they have between them. And then when it needs to be used, then we add on top of that this generative AI to make more specifically friendly for the application on the end user. So we are concerned about not only the compression I said before, but also the reasoning. And then the reasoning part is actually not only a thing to be able to adapt to different AI domain or different context, but also the thing to evolve over time, so be able to do more while after some time of communication. Actually, here comes a paradigm I will share at the end of this presentation was actually the thing that with this continuous learning, transmitter and receiver over time learn how to communicate and align in the way they communicate together. Just to give a flavor of some results we have, here is an example of text data, which actually is the easiest one, the way that, I mean, the one we don't have the most impressive performance results. We also have results ongoing now that will publish soon in the next delivery in month 18, so it means in June, for video, okay, where we show that we go either to a factor of 1000, but here you still see that actually we have roughly a factor of 200 of compression gain. But where comes this gain? For one part, the way we represent the data. So actually in this case we use graph based representation, and then we see that actually we can use less nodes in the graph to represent the same amount of information, but also the precision of each node. So roughly the size of the latent space we need for each node to be transmitted and represented actually can be notably reduced. So these two compression factors that goes together drives to something around 200, factor of 200. Then we also saw that using this approach, so doing this kind of semantic continuous learning, we can speed up also, we can reduce a lot the training needed. In the case of text communication, again, is easier than other cases because there's already a structure and so on. So actually, where the results are not as impressive as with the video or as with image, actually we already show and demonstrate a factor of 23 of reduction of training period. And then the third example, it's something that's more to the physical level. We show also how, by using a semantic robust communication, so by having this additional layer of protection, what we have is that we can, if you take the case of a reconfirmable intelligent surfaces, okay, we made an example. So we compare the semantic approach with a classical encoding approach. Then we see that actually to achieve say the performance target, which is about around 90% we can have in this kind of inference process, we need not more than 40 something percent of the surface, the RS, while in the same kind of scenario where even using the full surface RS, still we have not reaching the final target performance of the system. So this actually means that we can use roughly 1/5, 1/6 of the resources. This case is the surface of the antenna, but it can be other kind of resources, thanks to the semantic gain. We have also two important proof of concept. One is more the physical level, where we show the point-to-point scenario. We have a transmitter and receiver, and roughly we show how this source and channel coding with semantic communication improve the performance against the classical approach. And the second one, we have more the context of collaborative agents. In this case, collaborative robots have to do a common task together, like for example, bring some package they can do by themselves. So they have to federate, move tables together, and so on. And then we do that through the exchange of semantic messages, but also by reconstructing and localizing objects through what we call semantic maps in the environment. And actually, to close this presentation, actually, I would like to bring you to the flavor of what we have on this continuous training in the semantic communication. Is like in a couple that are sharing a piece of bread. That's very classical case in French system, where actually the first meeting, they introduce each other very precisely, very candidly. They probably describe what they want, and they thanks each other after the exchange. Then after this actually is the classical case we do all the time with this content blind communication. We always start from zero in the communication with transmitter and receiver. Then actually after several months, this couple know each other, so there's a brief introduction. And actually they ask with the describing the request, but I mean with not too many details. And there's a brief thanks. Then after several years, there's no introduction. Expect each other to do what actually the action that's required, and the request is with a very short description, and there's no thanks at the end. And after a whole life, actually, the couple is just able to hear each other, and they just with a very quick eye contact they actually understand each other what they want. There's no thanks, just wait for the next communication. And actually, I would say this is really the path between the content-blind communication and then with this training of the model incrementally over time, you have those EA-native semantic communication in which actually you just need to send the complement of what cannot be understandable, but you construct and align the intelligence to work together and understand each other. This actually closes my presentation. I give you some reading here on what we did. There's also a recent paper have been published on Nature, and there's another one, second on Nature, coming by the end of this year. Is under review at the moment. We have this paper actually represent the overall concept and the key parts of our project. Some other technical one. If you want, you have our LinkedIn group, our website, and you can always contact me and our project coordinator for any questions. Thanks for your attention.
Yeah, thank you, Emilio. So for your presentation, when you are presenting to us on semantic communication, in that communication, I think you are not using very much semantic communication, but you are telling about that. But we need some more improvement in this communication channel and the experience to take steps on that front. I don't see any immediate questions in the chat. I don't know if somebody wants to raise your hand, and we have Kuntal raising your hand, so please.
Hi, this is good progress. One question is that, do you envision any work in the radio layer to make this more robust?
Okay, so thanks for the question. Hi, nice to see you again. Yes, we do actually work on the radio level. We have so for example, we are working on semantic waveforms, for example. We have works on this semantic, say, adaptable antennas. The example is RS and other things. So we do actually now work on the angle of how resources needed at the physical layer can be reduced or can be more unreliable thanks to the robustness introduced by the semantic communication. Does it answer to your question?
Yeah, it does. It does. I think some more follow-up is needed. I don't want to take all the time, but I think there are a lot more questions I have to clarify. But,
you can actually send me an email. We can set a call if you want.
Sure. Thank you. Thank you very much.
Now there is also in the chat, there is questions. If you could take a look at that, Emilio.
Okay, just one second. I don't see the chat anymore because I'm in presented mode. How to do
when you are exiting that, so
just one second. I mean, you mean after the call? Because I don't see any more chat.
After presentation, yes. But I would propose then that we move forward in the presentations and hear then about a new Lighthouse project, Sustain 6G. And Christoph, the floor is yours.
Thank you very much. Can you hear me?
Yes, we can see and hear.
Very good. Just 1 second. I should be able to present, hopefully. I hope you can also see the slides.
Yes.
Interesting. It started with the last slide, which was not necessarily intentional. Now we are at the first slide. Okay, very good. Thank you very much for the opportunity to provide the Sustain 6G project in this forum here. So my name is Christoph Schmelz, Nokia in Munich in Germany, and I'm the coordinator of Sustain 6G, which is, as you can see from the title, Sustainability Advanced and Innovative Networking with 6G. It's denominated as the Sustainability Lighthouse project, and this project has just started now in January, so we are brand new. Some quick facts and figures about the project. The links are also available in the PDF, which I made available, hopefully to all of you. So as said, me being coordinator here, we have Olivier Boucher from Orange in France, who took the role as technical manager, and Tassos Gavras from Euroscom, who took the role as innovation manager. The project has started on 1st of January, and exactly 4 weeks ago, we had our kickoff meeting at Orange. Project will run for 2.5 years, so till mid of 2027. And compared to what we have just heard from Emilio, we are not halfway, but as said, we are just in the very beginning with a consortium of overall 24 partner organizations from 10 European countries. And maybe something which is quite important to see also in this context, that we have a quite large number of SMEs participating in here, representing various aspects of sustainability. Budget and effort is maybe not so important at the beginning. The website, by the way, is already available or online already since mid of December. So we were a bit premature here, but it was also good to receive first feedback on the content. Now, about sustainability, what does it mean, or what are the key questions in the context of 6G, which we would like to address as part of the project? First question is, and that is prone to be a very challenging or lead to challenging discussions, what actually is sustainability? And in the end, then, how can sustainability be quantified? Or at least qualitatively described. So as kind of initial questions we started with. Then next point, how can 6G help to make vertical applications more sustainable? And what are the technical enablers that we need to look at to make 6G more sustainable? And in the end, for sure, when it comes to the implementation of 6G, or at least recommendation and guidelines, how can sustainability be implemented in the end? And what do standards need to do, but also what does regulation, or maybe even in the context of policies, you could even say politics, need to do to fully integrate sustainability in 6G? So this is the kind of baseline set of questions around sustainability in the context of 6G, which built the starting point for our project. Now, on the first question, what is sustainability? Kind of this canvas here, or you could even call it kind of a matrix. So sustainability has, at least looking at the baseline here, and that's the UN SDGs, 3 areas. That means economic, societal, and environmental. Most of you working on solutions that also drive, let's say, sustainability will particularly look into the environmental part. So when it comes to energy savings or energy efficiency or non-zero network. But sustainability is much more than that. So looking at societal aspects, for example, there are some kind of key topics like accessibility, which you could translate into coverage. For example, it is trustworthiness, responsibility, and in the context of AI, this is very much important. Also economically plays a key role, listening to many of the operators saying, okay, with 6G, we need to come back to a track where communication infrastructure provisioning is becoming economical viable again. And besides that, if you look then a bit more in the on the other side, meaning more into the vertical perspective, things we talk about here are digital and transformation of industry and also public services. We look into potential new business models from an economic point of view. We look into, from a societal point of view, privacy, data protection for applications provided by verticals. Also in terms of accurate information or reliable information. And for sure, from the environmental side, it's the same thing. Looking at the large diversity of vertical sectors, each of them has its specific environmental challenges, whether this is the carbon dioxide emissions or greenhouse gas emissions, whether it's impact to biodiversity or geodiversity, but also smart energy management. So from the overall perspective, the project will look at least into specific aspects out of this large picture, out of those 6 dimensions. And what is also clear, if you look at that, many of the requirements here have interrelations to each other. So you cannot look at vertical specific environmental challenges in terms of energy saving against the energy consumption of the network. So there might be a conflict here or a trade-off. You need to adapt. Simply saying the most energy saving communication network would be the one which doesn't exist, so which doesn't consume any energy. But this is probably not the way we want to go. So that is, let's say, the big picture we will be looking at. Now, what does it mean for the project? Coming back to the questions, we developed a, let's say, an overall high-level methodology, which we would like to address. And this is having 6 steps. So we first look into the sustainability needs, addressing the different dimensions of sustainability. Furthermore, we will look into the definition and assessment of sustainability metrics. So how can they be quantified? Looking into processes, looking into methodologies, how to do that at all, or where possible, into all sustainability areas. Then for sure we look at the let's say more technical points or the technical perspective in both areas. So on the vertical side, but also in the network, on the communication network side. Just giving a couple of examples where we will be looking at from a technical point of view, from the technical core of the project. In terms of the outcome, so the validation, the evaluation, but also in terms of the impact creation, there are 2 parts. So first one, the insights we get from the technical work, but also from the definition of the methodologies and processes. An outcome, key outcome will be to provide guidelines and best practice recommendations for the implementation. So here we really have the implementation perspective. But also the other side is what I mentioned beforehand, strategic roadmaps. So how should standardization, how should regulation evolve to make sustainability really a core of a 6G ecosystem? And all these together build more or less, just quickly, let's say the different industry fora, standards bodies, but also for sure the European context, where we see the key relevance for the work we're doing here. But looking at that, we get the key objectives for the project. So just a quick repetition of what was on the previous slide, and understanding really what these sustainability needs and values are. So that's not only looking within the consortium, so really reaching out there. We will look at what is already there, what is already in the table from the SNS projects, what is already on the table from international and European regulation and policies. And the key point is here that we, by the way, based on also the lots of the work which Hexa-X-II and other projects have done, consolidate that. We will also reach out to stakeholders which are outside the consortium. So, for example, through advisory board, but also our good connections from the consortium members to any kind of fora and third parties to collect such requirements. the definition of methodologies and processes for definition and assessment. That's something which will be ongoing throughout almost the complete runtime of the project. Here it is important to say we will not develop that one process and that will then never be changed anymore and will be used throughout the project and recommended to other projects. No, here we really you will use an iterative approach to see, okay, what is feasible and where we need to make adjustments to make it in the end also really applicable and implementable in the real world. Then the use case integration and the 6G technologies enhancement. I mean, there's lots on the table, in particular on 6G technologies or concepts, so we will not reinvent the wheel here, but we have identified a number of gaps which are still there, at least from an SNS context, we will be working on. And in terms of the use cases, here we made a selection. You cannot look at the complete or the whole plethora of vertical scenarios. So we will do a particular focus here in the project. And for that, what we did is selecting agriculture, e-health or telemedicine, and energy smart grids as the exemplary vertical scenarios we will be looking into. Key reason behind that is that looking at the requirements from those scenarios, they cover a quite large number of performance KPIs for the network itself, but they also cover a large variety of sustainability goals. Yeah, agriculture has a lot to do also with environmental impact, but also societal impact. Energy, societal, and environmental and economic impact for sure. So the idea behind that is that the results or the insights we get from looking into those vertical scenarios, we can extrapolate them also towards other vertical scenarios. So finally, then a key step or a key work of the project will also be to really validate and evaluate what we are doing here. So implementation of proof of concepts. Here we will also leverage the fact that SNS has quite a number of large trial projects and we have several partners who are involved there as well. So that we don't have to do everything on our own, but that we can also do parts of that validation and evaluation through collaboration in the SNS context. And then finally, the impact generation. Well, the usual dissemination, standardization, exploitation, but really creating those guidelines through, for example, socio-economic, techno-economic analysis in such way that we also have the competence in the consortium to put these facts together and provide guidelines to standardization, let's say strategy towards policymakers, how to, or recommendations, what from our point of view would be recommendable for the next steps in a sustainable 6G. By the way, in this context, also relevant is that we will look into business models. Hexa-X-II also did a good step already in this direction. We will continue this work, enhance this work, since we see this as particularly looking at the economic part as a key part of the sustainability work. Now, just very briefly on the methodology, that makes things maybe a bit visually easier. These initial steps, like the analysis on what's on the table, analyzing the state of the art, doing the technology collection, distilling the use cases, not only ours, but also looking what else is on the table here, identifying the sustainability needs from the different stakeholders, from the different sources. So this will be the key part, the initial step of the project, and this is where we have already started with. Then we have, let's say, two loops which are running in parallel, but which are also interconnected. One of them on the use case design, 6G for sustainability. So looking into the vertical sectors identifying what are the key requirements for communication technology to be implemented, but also leveraging maybe additional use cases in vertical scenarios that can be enabled through 6G technology. And the other part is the 6G technology enablers themselves. So the topics we'll be looking at. I have one slide coming up where we go a bit into detail about that. And then it's really about integrating them. So in the proof of concepts, we don't want to run this in parallel and then we have a nice result. No, the key point is that through iterative processes, and this is why we have these three circles around here, that at least exemplary, we look with implementing 6G technology enablers coming from within or even without the project into the use cases and see, okay, what kind of gains in terms of sustainability values we can really achieve by that. And finally, something which is very important, which I mentioned already beforehand, you cannot look at let's say a handprint or a footprint, or you cannot look at a vertical ecosystem and the communication ecosystem separately, because in the end, sustainability is needs an end-to-end perspective. So really from the device, through the communication infrastructure, through the service infrastructure, to the application, to the vertical application. And each of the parts in there will have different sustainability goals. They may have separate, different specific metrics that can be measured. But what is interesting in the end, that the end-to-end, the overall sustainability impact or improvement can be optimized. And for this integration is crucial to be done. So this is something which we really aim at as part of the project. And not only theoretically on paperwork, but really doing this in terms of proof of concept implementations. Yeah, and then as mentioned, finally, the insights we get from that, so from the various implementation circles, provide that and the evaluation results for the technology, for the processes, for the methodology behind, put that into the best practices. And reach out for sure. I mean, standardization output. As you know, 6G standardization has already started. At least it's in its initial phase. Work is running at ITU, work is running at 3GPP, work is running at ORAN and others. So direct technical results will be provided to there, but also through our partner organizations. But as said, we will also be reaching out to the large amount of industry fora, which go beyond, let's say, the direct technical standardization. And for sure, we will also collaborate with the European Commission on these topics. And there's a quite strong interest from their side on the results we're going to deliver. Yeah, just a few numbers. We will be looking into, or we have pre-identified at least 9 use cases from the consortium members and 16 innovations in the technology. And I will quickly go on that in the next slide. So very roughly, we will be looking in RAN evolution topics, end-to-end solutions and network management. So this also includes, and not everything is completely listed here, looks into core and cloud infrastructure topics. AI for sure, artificial intelligence is also a key part here. And network management, since if you look at an end-to-end system, let's say the management part will also play a key role in the end. But we will also not only look into wireless technology, but also optical technology, since there's quite a large number of use cases looking at industry, but also looking at e-health, for example, where fixed connections may play a role. Here a bit more on the vertical scenarios we look at, and some of the examples of the particular use cases we'll be looking at. From an agricultural point of view, this is on the one side related to vehicles, autonomous vehicles. It's about data and information creation and provisioning, but it's also on the topic of connectivity. And this is a good example, connectivity on demand in rural areas. This may not only apply for agriculture, but it may also apply for quite a number of additional use cases in completely different scenarios. E-health, same. Some topics are related to maybe a more fixed or with a static location. Others with the requirement on mobility. And on the Medical Data Federation, here we go into the topic of privacy, security, trustworthiness, which is very important looking at the global or overall sustainability context. And in terms of smart grid, renewable energies play a more increasingly important role in Europe, at least in quite a large number of countries. And looking at them into the future, how to make them more resilient, how to do a planning, how to be quickly reactive. And that is something which goes in line with the communication infrastructure. Since just a simple example, you have a power failure and your smart grid relies on communication infrastructure to be functioning. So how do you boot up the network again? The network, the communication infrastructure has no power, so it's non-functional, and the smart grid has no communication infrastructure. So how to boot it up? So that needs to go in line. And this is some of the quite interesting use cases which need to be addressed here, for example. Now, as mentioned, you need to look at it from an end-to-end perspective as a whole system. So the question is, how do we solve that? How to solve the challenge of exchanging data between the different stakeholders in the system.
Christoph.
And yes, this is the almost last slide. Yeah.
Okay. Yep.
Yeah. How do we solve the issue in connecting these stakeholders? And here we will go for a sustainability management plane concept, which drives that. And just as a quick hint, how interconnected all these topics are with the different sustainability parts, and this is by far not a complete picture. So looking at these trade-offs will be really a challenge in the end. I step over that now. Just a quick on the timeline. We are now in the initial phase, initial concept work. The core technical work will run for the remainder of this year and next year. And then the consolidation of results will be done in the first half of 2027. That's it from my side. Thank you very much.
Thank you very much, Christoph. Very central theme, sustainability. I don't see any immediate questions to you in the chat, but and we are, from the timetable point of view, we are at the time of the break. But if somebody wants to use the break rather for raising a question, so fine for me, please then raise your hand.
So you can for sure reach me by email anytime. We also have, I said the website is online. There's a contact opportunity also through that. And maybe as a quick hint, we may reach out to all running projects in the near future, because as I said, we would like to build this ecosystem with respect to sustainability, and we are strongly interested in results related to sustainability, but also proof of concepts that have been conducted. So this is a bit of a pre-warning that you may be approached by us on potential input to our project, since we will be really relying on you with existing results. Thank you. Yeah,
thank you. So good to looking forward to the interaction more among the projects. But then I would propose that we thank Christoph once more and announce that we have a break. And proposal is that we stop the break in 30 minutes. So we start back again at the 25 minutes to the next full hour. So here and see you soon.
Thank you.
Jeroen, as we soon start officially, maybe you could already start sharing your slides also to test that it goes fine. So certainly it should go as you have been doing that in this context before.
Yes. Can you see the slides and hear me well?
Yes, can hear you well, see the video and see the slides. And let's wait for a short moment until we get to this 25 minutes. So.
Perfect.
Okay, I would propose that we then continue and we come back to Hexa-X-II and give the floor to Work Package 5 lead Jeroen. So please, the floor is yours.
Thank you, Mikko. So yes, I'm Jeroen Famaey from IMEC in Belgium, and I'm leading Work Package 5 in Hexa-X-II. And this work package is about future devices and flexible infrastructure. And within the work package, we study 4 main topics. The first one is looking at the requirements of future 6G use cases, and based on those requirements, identify new types of devices and classify and characterize them. And then we design technologies that will help achieve the requirements of these devices, looking first at transceiver design. So this includes both low frequency transceivers like FR1, FR2, FR3 band, but also novel sub-terahertz transceiver architectures. Second main technical topic we are looking into is system on chip, so extending the capabilities of future devices and base stations with new trustworthy and modularly designed system on chip components. And finally, we have a focus on very low power and specifically energy neutral devices, which is a new type of device that is expected to be included in 6G. And the work in Work Package 5 of Hexa-X-II is actually slowly coming to an end. We are now finalizing our last deliverable, which is deliverable 5.5, and will be publicly released very soon in April this year. And here you can see the final classification of devices that we performed. And as you can see, we have both an enhancement or evolution of existing 5G device classes, which are shown in purple color. So that means enhancement of enhanced mobile broadband, enhanced massive machine type communication. And we also looked into enhancement of ultra reliable low latency communication, but no use cases could be identified at the moment that required an enhancement of the existing requirements of URLC. We also identified 3 new classes that extend the capabilities of 6G devices. The first one being energy neutral devices, which have very low data rate, have no strict reliability or latency requirements, but a very stringent energy requirements and even rely on ambient energy or energy harvesting in general. And this is useful for very low power sensors that need a very long lifetime. Another new class is the reliable high data rate with bounded latency, which has data rate requirements up to gigabits per second, like enhanced mobile broadband, but combines this with more stringent reliability and latency requirements as well. This is, for example, something that could be expected from wirelessly connected extended reality headsets. And the last one is high reliable and low latency, which has more stringent requirements in terms of reliability and latency than the other class, but also lower data rate requirements. And this is something that could be needed for collaborative robots. And then we investigated several technologies to achieve the requirements of these new and existing enhanced device classes. And the first technology we looked into is transceiver design for 6G. And we did hardware modeling, which is useful for example, research on new modulation techniques, signal processing, and radio design, which is also part of Hexa-X-II, but in Work Package 4, which was presented before by my colleague Ahmad. And we looked at power amplifier models for the FR2 and also the new FR3 frequency band, where we looked at the nonlinearities, comparing different model types and looking at their accuracy. We also studied what are the complexities that will pop up when designing power amplifier models for the FR3 band. And this is, among other things, the higher output power per power amplifier. Also, the fact that the power amplifier will be integrated with other components and advanced and new types of topologies. And we also studied hardware non-idealities and created models for that for sub-terahertz band, which has some unique difficulties. We looked at non-idealities of different components, such as a power amplifier, nonlinearity, imbalance in IQ, digital analog and analog digital conversion accuracy, phase shifter accuracy, and we also studied phase noise. And specifically, we developed power amplifier models considering the nonlinearities in the D band, looking both at memoryless and memory-based models. In addition to modeling, we also looked at the dimensioning of the transceiver architecture, looking at the energy consumption of both analog and digital components, and this showed that at higher frequencies, especially sub-terahertz, the digital component power consumption will relatively increase. We studied different beamforming architectures, fully digital, hybrid, and fully analog, and also looked at the trade-off there between throughput or data rate, power consumption, and energy efficiency. And this showed that actually you can achieve a much lower power consumption if the data rate can be limited, which is for many use cases the case, because, for example, 10 gigabits per second would be enough for many use cases, which consumes much less power than a transceiver architecture dimensioned for 48 gigabits per second, as shown in these two example figures. Another big issue at very high frequencies is the wideband phase noise, and we looked at techniques to mitigate this. In previous work, we already studied this in simulation. We developed a technique to introduce delays in the local oscillator local oscillators, and these delays then reduce the wideband phase noise. And now in the last deliverable of Hexa-X-II work package 5, we actually are experimentally validating this approach and showing that it actually works in practice as well for transmission at D-band. We also developed prototypes for reflective intelligence surfaces using FR2 frequency bands. We manufactured a 16 by 16 antenna element wrist tile and control interface, and we calibrated it and compared to simulation results, and show a very good match between the real life measurements and these simulations. And another topic of investigation was then looking at how these RIS devices could be integrated into the network. We looked at the control interface, so what kind of capabilities can the hardware expose to be controlled by the network or by devices in the network. But we also looked at standardization aspects and how existing standards for network controlled repeaters could be reused for RIS. And we saw that there's a lot of similarities between these two types of devices, but some additional standardization would be needed to include RIS control interface. And that brings me then to our work on trustworthy system-on-chip components. Within the project, we developed a secure and scalable SoC architecture that allows integrating different SoC components. We developed a trusted communication unit that enables the safe communication between the components on the SoC, and also an accelerator support module, which then allows integrating different types of hardware accelerators, such as, for example, an AI accelerator chip or a digital signal processing accelerator chip. A test chip was produced, and we performed area and power consumption analysis of which you can see some results on this slide, showing power in the order of milliwatts. And as we looked into how to integrate such hardware accelerators, we also developed accelerators for AI processing and signal processing, which are useful, for example, for AI-based radio design, where a base station and a UE need to use AI for radio communications. And then these accelerator chips allow to perform these operations at much lower power consumption than doing it in software, for example. And the final topic, as I mentioned, was energy neutral devices. So we studied specifically this new device type. This is now also a topic of in standardization. For example, in 3GPP, in release 18, they will include ambient IoT, which is a standard to support such energy neutral devices and to allow them to connect to the network. And the first aspect we looked into was energy harvesting, because as I mentioned before, energy neutral devices, they rely on harvested energy to power their operations. And we looked both at ambient harvesting and also at RF wireless power transfer. In terms of ambient harvesting, we developed a multi-source harvesting circuit, a power management unit that is able to combine energy from multiple sources in order to increase reliability. For example, it could combine solar energy with temperature gradient energy or with vibration energy. It has a very low power consumption and high efficiency, and it's able to store the energy, the harvested energy, in a capacitor bank that can be dynamically configured for optimal operations, depending on how much energy is being harvested and how much energy is being consumed. It's also able to monitor the incoming and outgoing energy to allow energy-aware operations of the device as it gets a view on the real-time harvesting and load performance. In addition to ambient energy that can be harvested from the environment, we also looked at how to extend the 6G infrastructure to support wireless power transfer using RF energy. So in that case, you would integrate power beacons into the 6G infrastructure, and these power beacons can wirelessly transfer energy over distances up to tens of meters to low power sensors that are deployed in the environment. And we studied how RIS and dynamic metasurface antennas can be exploited to improve the performance and the coverage range of wireless power transfer. And there it was shown that we can reduce the power consumption of power beacons using RIS or DMA compared to traditional antennas using digital beamforming. Our results also showed that a RIS with only 2 control bits per element gets performance that's very close to continuous phase shift configurations. We also studied here how movable antennas can be used to improve performance of RF wireless power transfer. We also looked at the trade-off between costs, materials, and performance, and we developed a methodology for sustainable manufacturing of printed electronics, which are widely used for low power, batteryless, and energy neutral devices. And this methodology combines the selection of the materials, the printing of the circuits, and the post-processing aspects. And it was used actually to manufacture a multi-antenna backscatter device as a proof of concept, which was then also used for research in the project. We also developed models to assess the energy consumption and costs of the enhanced massive machine type communication devices, consolidating different cellular IoT modem models, calibrating them with real measurements, and also looking at the component and device costs of different technologies. And this model will be used as a basis to design new communication techniques for even lower power devices and to optimize the operations of this type of devices. For example, in one study, we used the models to compare different synchronization methods for energy neutral devices that have very long sleep cycles and where synchronization becomes a problem due to the long sleep. And finally, we also looked at how to optimize the network to be able to support these energy neutral devices, as existing protocols in 5G are quite power consuming. They require a lot of signaling, which is hard to achieve when you look at energy neutral devices. So we compared different channel access methods to see how they performed in terms of energy consumption and scalability, comparing traditional random access with fast uplink and ground-free channel access. We also developed a user plane solution that allows connecting energy neutral devices to the network with less signaling overhead and less need to maintain state. And the advantage of this approach is that it can be integrated with legacy network solutions. So it doesn't require a completely new complete overhaul of the network infrastructure, which of course is a cost-saving method. And finally, we looked at how to make the scheduling protocols for uplink and downlink communication energy aware, so that the schedule can adapt to the availability of energy on energy neutral devices, as these devices have very limited energy, but also very variable energy over time. Finally, we looked at optimizing the duty cycle and making use of wake-up radios to improve the operations for networks with a lot of sensors, where these sensors want to sense events that occur, but these events have spatial and temporal correlation. So then it can be exploited by the network to only wake up certain devices when an event occurs and collect information in that way. And we looked at the trade-off between the energy consumption of the sensors and the detection accuracy of events that occur. And based on the work that was done in work package 5 of Hexa-X-II, we also contributed to the integrated proof of concepts in the project. And we looked at two types of devices. The first one was integrating extended reality headsets into cobot proof of concepts, where we looked at offloading computational capability, computation tasks, such as the rendering task to an edge server, and also looked at adjusting the application data rate to the availability of radio and network resources and changing conditions in the network. The development of this proof of concept is still ongoing, and the results will be presented not in work package 5 final deliverable, but in the deliverable on the proof of concepts, which is due at the end of the project. Another POC is focusing on energy neutral devices, and specifically zero energy devices without batteries that use ambient backscatter. So ambient backscatter means that they collect radio signals transmitted by another device, such as, for example, a UE communicating with a base station, and then remodulate those ambient signals to transmit some limited information to the base station. So that means that they don't require a dedicated reader, which saves power and cost compared to a backscatter that uses a reader, like, for example, RFID. And these devices, backscatter devices without batteries, can then be used to localize users in a building, for example, so that avoids the need for beacons or tags with batteries to do indoor localization. And a real prototype, an actual prototype, was developed that can work with commercial mobile phones and a custom LTE or 5G base station that was developed based on SRS RAM and QMI core network. And with this work, we contributed to some of the quantified targets of Hexa-X-II, such as achieving access links with very high rates over 0.1 terabits per second. This is mainly with the work we did on sub-THz transceivers. Reducing the energy consumption per bit in the network. We optimized transceiver design and transceiver architectures to be more energy efficient, but also looked at ways to improve energy efficiency with very low power and energy neutral devices. And finally, we contributed to the reduction of operational costs of the network by looking into RF wireless power transfer to avoid battery replacement costs, and also looking at ambient backscatter to avoid the need for dedicated reader devices. So yeah, our work has already been made available in 2 public deliverables, which are available on the website of the project. So deliverable 5.2 and 5.3. And very soon we'll have the final results, some of which I presented here today, available publicly in deliverable 5.5. So be sure to check this out on the Hexa-X-II website. Thank you very much.
Thank you, Jeroen. There is one question in the chat. Maybe you could take a look at that.
I'll do that.
If you look at the time allocation, so then we would be moving to the next presentation. So thank you very much, Jeroen. And the next presentation is on Sub-THz CMOS phased array transceiver design in CMOS for 6G by Okada from Institute of Science in Tokyo. So please, the floor is yours.
Okay. Hi, I'm Kenichi Okada from Institute of Science Tokyo. Okay. Can you hear me?
Yes, can see and hear you well.
Yeah. Okay. Yeah. In this presentation, I'd like to share about the recent progress of, especially about the device size.
Sorry, concerning the slides, are you?
I try to share. Well, you can see. Okay, I will try again. How about this?
So sorry again. Actually, now I need to. I did already raise earlier you to allow present, but I need to redo that. Just a moment. So now you should be able to share.
Yeah. Okay. I'm sharing. Still, you can see.
No.
Okay. How about this?
Now it is visible. Yes. Thank you.
Okay. Yeah. Okay. I'd like to start. Okay. In this presentation, I'd like to share about something Sub-THz CMOS phased array design. Okay. Maybe you know now cellular communication and Wi-Fi started using the millimeter wave, but you know it is not very much mature. But still, for considering long term, the very high speed wireless communication is required. This trend is showing about the mobile traffic increase in Japan. It is roughly 1/130 of the worldwide mobile traffic, but still it is increasing. So as a circuit designer, we have to support this kind of huge increase of wireless traffic. So many people started considering to use millimeter wave and sub-terahertz like 150 gigahertz D-band or sub-terahertz, some higher frequency like 300 gigahertz. In that case, the communication distance becomes something shorter. Okay, such a trend can be easily understood by using this kind of equation. The communication distance can be explained by transmitting power and the gain and the carrier frequency. If we keep the same omnidirectional communication, in that case, the communication distance becomes something like this. So if we keep using the omnidirectional communication, the distance becomes shorter. So we need this kind of phased array. This one is designed for 5G base station, collaborating with NEC, Japanese the telecommunication company. The time this is for small cell communication using 28 gigahertz, using a 64 element antenna. In this design, all beamformer is realized by CMOS technology. CMOS is basically used for digital circuitry like processor, SOC or something. But still, it can be used for this kind of high frequency design. It is one of the most important to lowering the fabrication cost and power consumption. So it is a key enabler for the future 5G or 6G technologies, I think. Okay, this is first thing. This is about only 28 gigahertz side, but there's still a 5G 28 gigahertz band is not very satisfactorily for many users. For example, this explaining about link budget for 28 gigahertz for downlink side. At 28 gigahertz, we had only 400 megahertz. Even channel bonding, it became 800 or something. Still, in that case, the data rate is very limited. For example, if we use the 256 element antenna from the base station, and usually the user equipment have only 4 or 5 antenna. In that case, the downlink can be okay, but uplink became very severe. For keeping the 500 communication distance, in that case, the only 64 QAM can be transmitted with 1.26 gigabps, considering the TDD and 5 overhead. In that case, the uplink also have a very severe situation. The power is not delivered, power is not enough, and the time slot for TDD is limited, and so the data rate becomes something like this. So for considering 6G generation, we have to consider the much higher, but faster data rate using the sub-THz or even massive MIMO technology for millimeter wave, not for 6 gigahertz. And NTN, I skip that NTN things. But on the other hand, to make this kind of device technology mature for future 6G system, in that case, lowering the fabrication cost and lowering the power consumption is really important, especially for handset side. So the main target is actually many hardware people are considering lowering fabrication cost, how to make it cheaper. And sometimes it is depending on the circuit architecture and the transceiver architecture, and lowering power consumption also important issue. Then okay, for example, this is about 28 gigahertz module, have roughly 20 by 5 millimeter size. On the other hand, if we use, let's think about 150 gigahertz, in that case, the carrier frequency becomes 5 times higher, wavelengths become 5 times shorter. In that case, if we have the same aperture size, 5 by 20 millimeter, in that case, we can place the 5 by 5 times larger number of antenna. In that case, even using the same aperture size, we can have like 100 or 100 element, even the same size, same area. So at the same time, the 150 gigahertz have a very wide frequency bandwidth, roughly 25 times wider spectrum can be used. In that case, okay, this is actually based on the real transistor characteristic, like noise figure and output power and the power consumption based on our previous design. In that case, let's thinking about comparing with the 30 gigahertz and 150 gigahertz. In that case, the frequency bandwidth is roughly 25 times different. So data rate also became 25 faster using the D-band frequency. And keeping the same, as I explained, we have, for example, 100 millimeter square aperture size. In that case, the number of antenna became 25 times higher. High density antenna.
You connected to the workshop? Yeah. This guy from Qualcomm is explaining some that sounds
Please
from
mute
Japan
yourself if you are not the presenter, but I'll also mute yourself.
Okay. Number of, even decreasing transmitting power from each power amplifier, the total power consumption became 500 milliwatt. But on the other hand, if we keep so have some duty cycling operation, if we need only 1.6 gigabps, in that case, more than for long time, this kind of transmitter can be turned off, for saving the power. In that case, average power consumption becomes 200 milliwatt. So even using the millimeter, the D-band frequency, power consumption can be reduced a lot like this, even with a longer communication distance. But this is for thinking that in case of 30 gigahertz, distance become 480. But if we think about same distance or 480 meter, that case the number of the antenna for user equipment size become only 20, and the power consumption become 40 milliwatt, 9 times smaller power consumption. is required. So what I want to say here is that even longer communication distance and longer power consumption can be achievable using this kind of D-band frequency. So yeah, actually this is based on the real CMOS design. Then I'd like to talk about something different side. Actually, maybe I'm this kind of areas person and mainly working for the transceiver design using CMOS IC technology. Maybe you are not very familiar with this kind of hardware design, so I will skip the detail. But even using the CMOS technology, the 65 is actually not very advanced technology. It was started 10 years ago. It is a kind of very cheaper, reasonable price technology. But still, even transceiver can be designed using this the cheaper mass production ready CMOS technology can be usable. And in this case, this design can support 114 to 170 gigahertz frequency can be covered. Actually, very wide frequency boundaries can be maintained by using this CMOS technology transceiver. And the baseband and the mixer and the 4RF chain can support this wide frequency range, even supporting the phase array. For our next design, that is further supported phase array. So then this chip micrograph, it is very cheap, small, and have a waveguide interface directly connect to the whole antenna in this design. And waveguide transition is also integrated in the PCB side. Very mass production ready, only mass production ready technology is useful in this transceiver design. And this is a measurement result and measured at lab environment. This is for 1 meter communication distance. And also we borrow some an acoustic chamber. The more than 15 meter communication distance is measured. This is the upper limit for because of this room size. But we could realize very fast data rate in terms of communication distance. If we have, we will have a 100 gigabps more than 30 or with reducing the data rate, the more than 100 communication distance can be realized by using this transceiver, CMOS transceiver, even a single stream one. And in terms of data rate, we can in this measurement we have only 40 gigaball because of this is limited by the measurement equipment. But still, we could realize more 200 gigabps could be realized with some enough margin of EVM characteristic. So this fast realization of 200 gigabps by using the CMOS technology. Then we tried to realize MIMO communication. In this case, it's a little bit messy, but the whole antenna is priced closely, and the H and the V and the V and H placement for transmitting side and the receiving side. And in this case, distance is not that long, but the DP MIMO, dual polarization MIMO, and loss MIMO is combined. And the data rate is something like this. The 160 gigabps for each stream could be realized. In this case, the whole stream is transmitted at the same time, and they're received at the same time, and they're modulated. In this measurement, we use a very high-speed oscilloscope, transmitting and receiving at the same time, and could realize in total 640 gigabps could be achieved in this design. So now I think in terms of data rate, so this kind of very wide boundaries and the fast modulation can be possible using CMOS technology. And for the next step, we're considering to make it the phase array for longer distance, more than 1 kilometer communication distance. It is not very difficult, I think, just to maintain wide boundaries antenna and the height that is required, but it can be possible, I think. Okay, then this is explaining about something comparison. Very long distance and the fast communication could be realized even using the CMOS technology. Okay, then I'd like to a little bit introduce about the 300 gigahertz phase array transceiver also by CMOS technology. Conventional planar CMOS technology have some limitation of Fmax characteristic. For the performance index, there is Fmax and Ft. Unfortunately, the Ft can be okay. Ft is improved by the performance improvement of digital factory. On the other hand, analog is not the main target of advanced CMOS technology. In that case, the Fmax is something saturated around something like this. So we applying the layout optimization to extending this Fmax characteristic. We realize about 350 gigahertz Fmax characteristic by our own layout technology. So then we implement this kind of the phased array transmitter. In this design, the antenna is integrated inside the CMOS chip, and we apply some ion irradiation to improve antenna radiation efficiency. And CMOS power amplifier is fastly integrated. This is actually first time to integrate 300 gigahertz power amplifier with antenna and phase array components like phase shift. In this design, the error phase shifting architecture is applied, and 4 element is integrated in the same chip. Power consumption is actually not that large, about 150 or something could be realized in this design. And each IC chip have 4 element antennas, and one PCB have 4 IC. The 4 ICs that are implemented like this, and there is 16 ICs, and in total 64 element module could be realized like this. Almost half lambda pitch the phased array could be realized. So something longer communication distance and more than 50 gigabps data rate could be realized in this design. Okay, this is the conclusion of my presentation. Now the millimeter wave and sub-THz is, I think it's kind of ready for real service. I think still we have to solve the something issue of the minor issue, I think. But in terms of technology, CMOS is capable of this kind of millimeter wave and D-band and sub-THz communication. So but further energy efficiency improvement and lowering the power consumption and lowering the fabrication cost is still important. But it's almost ready for the mass production, I think. Okay, that's it from me. Thank you very much for your time.
Thank you very much. Nice presentation, Okada. So concerning the need of spectrum, it's difficult to estimate like the timeline when it would be needed, and also there has been compared to, for example, of course, the initial thoughts on 5G, there has been more attention towards lower parts. Any comments on the timing there?
Timing for what?
Timing for the need of then going to.
Yeah, even sub-6 gigahertz, less than 10 gigahertz, FR3 band can be okay for high-speed wireless communication. But considering the like long term, this kind of sub-THz, and also I'm working for lower frequency side. But long term, this kind of high frequency is very important, and especially for considering size or aperture size. In case of longer communication distance, like 1 kilometer or 10 kilometer communication distance, sub-THz must be much advantageous, I think. So I think all depending on the application, but I think less than 10 years will be required, even using the D-band frequency, I think, for real service.
Yeah, thanks. Haris, do you have a comment on this or some other comment? So please go ahead.
Just a question, please. So, Okada-sensei, do you have any kind of baseband processing that you also do, or that you actually try to send and transmit the bits over these RF chains that you are using?
Yeah, we are collaborating with some Japanese company, but it is not very easy. Very high speed A to D converter and D to N converter will be required. For 40 GHz bandwidth cannot be modulated from the baseband side. Some frequency interleaving or something will be required. Yeah, that's good. Yeah, good point. Yeah, thank you.
Thank you.
Okay. There is no further questions in the chat, and I would then propose that we move forward in the program. So thanks, Okada. And we move to Haris Kakaning and telling us about the AI for Phi. So please, the floor is yours.
Unmute myself, and I think you can see the screen. Let me just get my full. Oops, sorry. I don't know. Can you see this full screen now, or?
It is unfortunately in the mode of how it should be seen for the one who is presenting, so showing also the next slide.
Let me just see how do I do that, because
See if you can use a share screen. Find a screen that you want to share. Thank you.
yes, just to find my mouse on this monitor first, and then how do I? Sorry, I don't know how. Where is this option for me to change?
One option you could try is that instead of sharing a window or application, just share your screen where you see it yourself in a full presentation mode.
Second, please. Okay, so the problem is that I have an enormous screen, so I'm not sure if you will. I hope, let's see how this now works. Can you see everything nicely?
Unfortunately not. So yeah, we see it in the same way that there is also like the next slide being shown.
Just 1 second. Where is this option to change that? Just wait a second. Okay, sorry.
Change quickly to the.
No, it is anyway clearly better than it was, and like it's now showing it much bigger already now, and now it's perfect.
Perfect.
Perfect. A little bit better, or?
Yeah, now it's perfect.
Can you hear me?
Yes, we can hear you. Something that you don't hear us. So can the people in the call hear Mikko still?
Yeah, sorry, just a second. So you still don't see the.
It was the slides were perfect, but it seems that you were not able to hear us for a moment.
Okay, just 1 moment, please. Okay, now you can see the slides, huh?
Yes, we can see the slides and we can hear you. So please.
Let's start. So, okay, good. So sorry for a little bit of delay from my side. So let's talk about next generation communications and computing systems and requirements that I see for if we want to look into this AI implementation for the physical layer, so that we understand, is it really going to be a powerful tool, or is it going to be something completely exhausting and insatiable for us? But let me just share my thoughts first. So what the point is that we are looking into the convergence in the future between the communications and computing, in the sense that we see the blending of the AI into the different wireless infrastructures. So I will use in this particular presentation, I will use the interactive industrial applications as one use case that I can maybe use as an example to showcase my thoughts. So if we are looking into the future and where we are going as a society, it's definitely going to this immersive and interactive applications, where we are looking into the hyperconnectivity, looking into the beyond sub-milliseconds, now actually beyond sub-microseconds of latencies, We are talking about efficient computing, and that means we need to have the integration between the on-device computing and edge computing for learning and training. Then we are talking about integrated spatio-temporal localization and ambient intelligence, that we actually can sense the environment and integrate that and through the multi-sensor fusion mechanisms. Yeah. So what are the challenges that we are having and we will be facing? So these are the challenges that I have regarding the physical layer. So for everything above that, I really don't, may apply, may not apply, I don't know, but this is the only focus on the physical layer functions of the communication system. So let's see how that looks like from the perspective of, let's say, a 3D graph with respect to the symmetric throughput. We have the synchronization challenges and we have latency. These are the three aspects that I see that are quite important for the next step for us to continue, because we are talking at one side of the thousands of frames, thousands of signaling frames that need to be synchronized simultaneously if we want to enable these interactive, fully interactive and immersive applications. So this is not the case until what we had until now with the slow interactive VR, AR, and fully interactive VR. So these applications were able to manage couple of hundreds of frames to be synchronized together. However, we are talking here about a really mass scale of synchronization effort. However, on the same side, we are looking into while we are having these challenges of synchronization effort, we are looking at the synchronous or symmetric throughputs between the uplink and downlink, which have to go really on the terabits per second scales. And then the latency, right? The latency is there because we are talking about applications that are in real time, that are applications that are something that touch human experiences, and then we really have to go even beyond or below millisecond scale. We are going to the microseconds and nanoseconds of the scale. So this is where we are going into this era of sustainability, resilience of our next generation system. So what are the challenges and requirements that we have to keep in mind? So when we look at the physical layer, we have been seeing a lot of works and papers that will be implying a machine learning. Training was or not done at the edge cloud, and then inference was done on the physical layer. However, if we really want to integrate and have this AI native physical layer structures, then we have to have online training operation in real time happening on the spot. And that also on the second challenge is or requirement is that this sensing or the data acquirement that is coming from the radio application, for example, channel estimation, equalizer, the detector, the decoder, whatever it is, it needs to happen in real time. So this sensing and needs to happen following the training parts and the inferences in the real time and both for the physical layer. And then the last one would be then when we look at that's all of these, so training, inferences, then this data sensing, then the decision making. Decision making needs to happen really on the micro scale basis, because we are talking. A really simple example is that we have now in the OFDM frames, we have the OFDM symbols in the standards which are going to the microsecond scale. So we are talking about 16 to 20 microseconds of the duration of the OFDM symbol. So if we want to have any kind of adaptation on that level, we really have to go much faster for the decision making, and then also making sure that the energy efficiency is addressed regarding the on-device processing. So this would be the three major requirements that we should keep in mind. And let me just give you an example. So if we have an example of this cooperative mobile robotics, so we have robots that are actually detecting objects, identifying the objects. They are then we are doing the trajectory and motion planning. We then go and planning the synchronization of these two robots. Task is being executed, and this entire process. If you think about this, I want to break this down in some requirements and present to you in this little bit simplified form. So we have a single or multiple robots. We have this split between the left side means the physical location-based processing and communication, and then on the right-hand side is this edge cloud or communication network supporting this use case. So what is happening? We have AI edge cloud on the devices. So we have either in the cloud, either on the device happening, for example, object detection, collision avoidance, anomaly detection. That is just some simple functions. So each robot has a local AI done at a robot unit, and what is first requirement is on the fly updating of these learning parameters. That needs to be weights of the parameters, biases, all of this needs to be updated. Then we are talking about energy efficient and low operational latency for particular hardware dependencies on this robot. Not every robot will be the same. They will be different, even from the same model of the robot. The hardware itself is having certain differences. Then we are talking about decision making, right? The decision making on how and when to split the point of the selection, which part will be done locally and which part will be done in the cloud. So these are some of the challenges that we had on the local side. Now we are looking into the network part and this edge server, which can support high computing resources. So we have the communication within the robot. Yeah, the robot itself has a communication that needs to happen inside. Then we have the communication between multiple robots. We have the communication between the humans that are, or let's say the technicians that are on the shop floor and the robots that are collaborating together. So and then finally we have this communication between the robots or the entire use case floor or shop floor and the edge cloud or the base station and the network itself further on. So these are the requirements that we are setting up for us: reliability, low latency, everything goes down. And this is where we have to figure out how now this will work. And in the context of that, we start first with asking question, how much that would cost? How much all this infrastructure for AI that we have shown here locally on left side and edge cloud or cloud-based on the right-hand side of the network, how much that would cost? So if we put some simple calculations, so if we take the H100 GPU and we assume that it's only consuming 60% of our time in operations, then we can say that it will it will consume somewhere around 3.668 megawatt hours of electricity in 1 year. So that is equivalent. That was equivalent to one German household. That is around 2 to 3 persons house. Yeah, and if you would now multiply that with the couple of million of these 3.4 million of the GPUs that are planned to be sold by the end of 2025, then we are entering to this staggering number of 12,880,000 megawatts hour of electricity per year. So that means that this is, if you want to translate it to euros, it will be some 3,456 billion euros, circa. And city of Tokyo per year, for example, consumption of electricity, or Berlin, Hamburg, Munich, Cologne, and Frankfurt all together consuming all this energy. So these are just the feelings for you to get what does it mean when we employ only GPUs. LLM is the same, computing challenges with LLM. If you just follow some simple mathematics of 100 million users per week, use ChatGPT, they use just 10 queries a day, that they will end up with 88,400 megawatts per hour. So this is now not me going to preach that we have to go green and we have to go all of our efforts vain. No, but I just want to say that there should be other approaches and not only blindly following the cloud-based or GPU-based processing. So what we have been doing in this project, we have been involved in the 6GEM project as one of the 4 research hubs in Germany. 6Giyyarpuram project, industrial project with some of the industry project partners in Germany, incubators from startup perspective, and our XR technologies for the control and management. So let me just quickly go through these aspects. We have been looking into how do we solve these issues. Of course, we are in our context, we are baseband processing people, so we do physical layer performance evaluation, we do the physical layer design algorithms, and we are mostly interested now into the efficient implementations on the hardware of our baseband algorithms. So on the FPGAs, we don't do ASICs because this is a little bit above our capabilities. and then we are looking into the millimeter wave and terahertz communication systems in order to enhance this efficiency. So now, what else we have been looking into? So if we look at the energy efficiency that we have been talking, and we are looking into the machine learning, so we have been looking into the DNNs and CNNs models, different models, in order to enable this cooperative robotics. And we have been using the tests on the MP SOX with the ZCU 106 and for our testing, and then looking into the power consumption to be lower than the 3 watt. We have managed to reduce the latencies, power consumption, and this is all per node. Now the question is, when we scale up this, when this is scaled up on thousands of nodes, if the thousands of nodes will ever be feasible, then how much of the processing we can actually save in comparison to traditional or centralized cloud-based GPUs. So this is one way of how you can look at it. On the other hand, you can take a look at deep reinforcement learning methods and LLMs. So if you would place everything in the cloud, you could create an agent at the base station that can control the users below. Or if you look at the multi-agent scenario where you have multiple base stations, then the question is, how do we actually break down this centralization of the DRL agents, and then to avoid this massive exchange of the weights and parameters between the base stations and the cloud. So this is something that we have been very much busy with, and then the implementation of the distributed reinforcement learning algorithms that have shown benefits with respect to the energy costs and processing times. Then, if you look at the transformers and LLMs, what is now quite interesting in the recent months, of course, depending on the LLM architecture, the implementation may be different. Either you're talking only about encoder-based architectures, or decoder, or both encoder-decoder architectures. Then the different exploitation strategies, that also depends on your designs, right? You have either you go with the prompt engineering or RAG methods or fine-tuning methods. So, for example, if a fine-tuning method is done, that is a major challenge. Would be how do you from where you get this a data set that you will actually train the LLM model to look into this particular use case. That can be done either through some really sophisticated simulation strategies, or through the data that will be coming from particular implementation. But what remains still is the challenge of how do you actually generate this large language model? How do you train it? So and what will be the cost of it? That is the main issue there. So exploitation in from our side, what we are looking into the two challenges, that is the dynamic resource allocation for the LLMs and the channel estimation aspect of it, so that we see how one of these or both methods may be improved with acceptance of the large language models, particularly looking into the fine-tuning the exploration strategy. Then quite interesting in today still is the beamforming. Beamforming has been research on beamforming has been done for many years and decades, I would say. However, as higher we go in the frequency bands, the challenges still remain. Challenges even in the millimeter wave bands are with the tracking and dynamic changes of the beam. So maybe we are looking there into the traditional signal processing. However, we're also looking into the integration of the efficient machine learning or AI methods in order to, for example, predict the beams, predict the number of beams, and predict the width of the beam, in order to save the time that is needed to do the beam forming, or to do the beam management strategy, and to selection of the beams that you see here on these illustrations. So I would also say that another aspect is quite important, that is the control and management of the application and application integration into the wireless systems. So we have been also very much busy with integrating the augmented reality or virtual or mixed reality into the various applications, industrial applications of wireless systems, including beamforming, and including the mobile robotics. I would just highlight what we have been doing in the last 2-3 years, and where we have been going on different places with different industrial partners. And I would like to thank you, maybe save a little bit of your time, and hopefully have some discussion with you regarding these topics. Thank you very much.
Yeah, thank you, Haris. Certainly some challenges from the sustainability point of view at the same time when the sustainability is all the time more and more important, central. So whatever solutions, approaches we are bringing up, there needs to be balance with respect to sustainability. And the technology itself needs to be sustainable, as we have heard today, and also then we can see how we can help with the sustainability, with the technology, the sustainability of other sectors. And concerning then these challenges that you raised with respect to cost and energy consumption with AI, what kind of research you have ongoing to kind of solve that? Could you tell a bit more about that, or how do you see what way should we go?
Yeah. So from our side, actually from my side, we are looking into the more efficient implementations of machine learning algorithms on the hardware. So that means that the question is, what would be the trade-offs? So we are looking into the trade-offs between the performance and implementation costs, and the implementation cost is also energy efficiency. We are not only concerned with these large language models, huge models for the deep learning, but we are also considering the Bayesian networks. We are considering the implementation of the even regression models, depending on the use case that we are looking into. So in principle is the optimization of the algorithms on hardware that needs to happen, and that we see there the challenges that how to pack the model from the computer simulations, which is actually performing well on a very small scale, and then but either by pruning and then losing the performance that is achievable on the computer and GPU based or CPU based machines. Yeah. So this is more or less the way forward that we have been taking.
Thank you. So in the chat there is 2 questions to you, and now also everybody, so you can also raise questions on any earlier presentations today. So we can have a short discussion overall on the session today. But Haris, there is, for example, a question to you from Sylvain Gerbov in the chat on the very challenging timing requirements that you were raising in the microsecond range. Sylvain is asking that is there a need to have this timing between the local processing at end device and with edge on this 1 microsecond? And could you then maybe bit more open that?
Yeah. So first of all, with the edge computing, cloud computing, you will never reach this microsecond. That is impossible. Yeah? So why I'm saying this is because of the decision making. So for example, if you want to make an AI based resource allocation mechanism or algorithm for bit loading, and you want to make it in real time, so that means that you have to go down on the scale of 1 frame with whatever 15, 16 OFDM symbols inside, and then you can do either on the frame scale. So on the frame scale, we are talking about 1 millisecond or even less, and that is where your decision making needs to work. So if you have any kind of machine learning algorithm that needs to be retrained or trained or inference, everything needs to happen on this scale. So if you go even further on down on the level of the finer granularity of the OFDM symbol, then you have to go to the microsecond scale, yeah? And then that means that all of the processing and decision making that you have to do on that scale. Of course, for the companies, since I was also in the industry, for many companies, this of course does not make sense. But from the perspective of the academic research, we really have to push forward in order to find new methods how we can actually improve the integration of the AI with the physical layer. So this is one way of how I think like this. And then if you look at the company perspective, of course, they will be always looking for ways that they optimize their implementations. That means that you make sure that you have this block-based, for example, resource management, and that is something that now I cannot that part I cannot now discuss further. Yeah, but for the first part, I'm ready to discuss anytime you would like. Okay, I don't know that this answer to a question. I don't see the chat here. Sorry, on my screen.
If you stop sharing, so then maybe you could see the screen. And Sylvain, please.
Yeah, it's answered my question. Thank you very much.
Most welcome. Thank you.
Then Konstantin, you can also raise your question via audio if you desire.
Hi, Haris. Okay, what I was asking about is actually what kind of models can you hope to train on the robots? Because if we say you have low power on the robots and low computing capabilities, just what kind of models can you train there, and how good would they be compared to this cloud-based models that you have with all these resources that are there on the cloud?
Can you just repeat your name? I didn't hear very well. Sorry.
Konstantin. Okay, I'm Konstantin from Carlos Letero. Yeah. Just
okay.
What kind of models can you train? Like, what architectures are you using? Would you use decision trees, neural nets to do this kind of thing? Because you have constraints. Yes, exactly.
Are you talking about this? Yeah. Okay. So if you are looking at this, for example, mobile robots, it depends, right? It depends. Is it a small device or is it a huge device? Depending on the computational complexity, we have some devices that we are using. Some of our mobile robots are working with our models that are ported on, for the deep reinforcement learning, on 540 kilobyte of memory. Then on the other hand, we have some deep neural networks that are actually consuming much more, and we need to prune them. We need to really reduce them. By doing that, I mean these networks that are the connected layers. By doing that, we have been losing the performance, and then we were not able to meet the reference from the traditional signal processing algorithms. We were just doing much worse. So this movement from the CPU or from the simulated based models to the hardware based constraints that we have on these mobile robots or mobile devices, we were just going above the performance that was given by the traditional algorithms. So that is I don't know if this is what you are asking about, or this was your question, or?
Yes, actually that was the question. Just what kind of models were you training on this one?
So we were using the deep reinforcement learning, the deep neural networks, CNNs, RNNs. So we have been implementing all of these.
Thanks for answering the question. Thanks.
Welcome.
Yeah, and also others, feel free to raise your hand if you want to have a question, comment related to this or some earlier presentation. Seems there is no other immediate questions, and also then it's time to close the morning session today. So thank you very much for the presentations and for the attendance, for the active interaction. And then the continuation of the sessions would take place in a bit more than 2 hours. So then the afternoon session for today would be starting. So hope to see you then, and closing the recording and soon closing the call. So thank you.
Thank you all.
Bye bye.
Thank you.